Okay.
Learned that too. Okay, so
you can.
I need to start this again. I apologize, everyone, for the technical difficulties. We started the whole presentation and we were not on stage properly, so my apologies. Thank you for your patience. Thank you for coming. I will start again. Very happy to have Rick Mayo with us from TACO. Rick started his career in the hydronic heating industry as a plumber in 1977, and in 1981 he transitioned into a wholesale role. And over the next 21 years, he worked his way up to a regional heating manager and left to pursue a training technical support position with Uponor-Wurzbo. And since he joined TACO in 2015, Rick has made an impact as the Western product and application instructor through his training that stretches from Alaska to San Diego and all 4 provinces in Western Canada. And we're happy to have him nationally today and talking to us about domestic hot water recirculation systems. So thanks for joining us, Rick.
Glad to be part of it. Thanks for the opportunity. So you folks can already see my first slide, and it's quite descriptive in what it's about. Just a clarification that there's probably some, high-rise applications and little oddball type applications where what I'm talking about would not make sense, but for the most part, you can see what target we're after here. So I'm going to go ahead and jump in. Some of the bullets here is just understanding there's room for improvement within our industry. In the realm of domestic hot water circulation. And there's some things that have been popping up over the last probably couple decades, some problems and stuff. So we're going to try to make sure we bring that to attention. Okay. Ideally, as a pump manufacturer, we want these circulators to be sized appropriately. And there's some a lot of things that line this out for us, other than just industry standards. There's some manufacturers of products within the system that have created some guardrails for us, so to speak, and you'll see where that's going as well. Again, I'm going to talk about some simple design changes that might help get this accomplished much easier, and I'll talk about that. That has to do with the actual plumbing, the hot water side of the plumbing design, and we'll focus on that as well. And then we'll show you, there's other ways than what you think traditionally in doing multiple zones of domestic hot water. Most people think I got a big pump there and I put these balancing valves all over the place, and that's how I accomplish my end goal. We're going to show you an alternative to that too as well. So, and Mark and I had talked earlier. I'll give plenty of opportunity. I would just as soon take the question now than save it for the end, depending on how the session's going. So, folks, go ahead and type that stuff in, Mark, and I'll check with Mark on occasion here, and we'll try to get your questions answered. So most people know what domestic hot water is all about. I mean, realistically, we should be able to walk up to a hot fixture, turn the water on, put our finger under there, and have hot water, usably warm. That's somewhere around 105 Fahrenheit within 3 to 5 seconds. Okay, that's really what it should be. Some people think it's acceptable to have 10 seconds. And some people will say, hey, you're still within code at 30 seconds. So you see what it's all about. It has a lot to do with just convenience and not wasting natural resource and energy and all that good stuff. So most people know that already. Lots of different ways to get this done, depending on, the layout of the building. What are we doing? Is it new construction? Do we have total control of the design and layout, or do we have to deal with something that's already there and try to make it better with a Band-Aid or an afterthought, that sort of thing? Okay. This concept, this next little picture I'm going to show you is really the conceptual of what we're trying to accomplish. And so I'm saying the energy delivery concept here, you can see that I have a water heater, right? It's shown a tank style, but look at the energy inside and imagine, if you will, the energy from that water heater being taken out and directed in close proximity to everything that the hot water serves. Okay, so think of the systems that we're building as energy delivery systems that put the source right next to where you want to use it. In this case, it would be fixture groups. Okay, So I mentioned this a little about problems and room for improvement within our system. So this little slide, and again, these slides have come out of a presentation that was much longer, so I'm just pulling a few out here and there. But this segment we're going to talk about is so why is the system failing? Again, this is not just fear mongering. These are just pictures. You can see where I've got them from. I'm not sure how it's rendering on your end, but I've got a little fine spray hitting the side of the sheetrock here. I've got this little almost atomized little spray coming out of this pipe here. You can see that we're dealing with copper pipe here, and I'm not just going to pick on copper, people. In fact, Copper Development Association has some pictures as well as where I got this. You can actually see holes in the pipe from what we refer to as velocity erosion corrosion. Again, that sounds like schoolhouse rock, but that's kind of what it's called in the long term. So, like I said, not going to talk about hard pipe. I'm going to talk about flexible piping systems as well. There's some pictures that I've got from Jan Anderson at Mr. Peck's, just showing, this little spray here that's hitting up against that joist bay, and some sprays down that had been hitting the insulation and dripping through. Just these are some of the things, and these are just lookups, folks. I'm not going to spend a lot of time detailing all this. I think many of you probably have seen this. You folks that are in the service business have probably fixed things like this, but we need to focus on where it's actually coming from and what are some of the contributing factors. Here is a piece of polypropylene. Okay, so again, most products that are used quite a bit in our industry right now potentially have issues, and that's what we want to bring to light. Okay, cause and effect is the 4 contributing factors. Now, this is kind of how I've got my head around this. There might be other ones, and when we have opportunity to talk, depending on timing, you folks can bring up some other ones that you might have saw as well. I'll start with the first one that comes to mind, that elevated water temperatures, one way or another. And what I mean by that is either it happens by happenstance or it happens by code regulation, or one reason or another, we're starting to see elevated temperatures within the domestic hot water systems for various reasons. You can see here, I'm pointing over here for 60C. Well, we learned a long time ago, a bunch of testing done, that we can kill the Legionella bacteria in approximately 32 minutes at that temperature. And that number is significant. You can see this number shown over and over, 60C for you folks, 140 F for us. Anyway, hopefully there's a reason for that. Maybe somebody just turning up the thermostat or the aquastat on the heating device, or we got stacking within a vertical tank, the stratification of temperature, but somebody playing with mixing devices. One way or another, potentially we're going to see elevated temperatures, and that's one of the contributing factors. Another one is, of course, the speed at which the fluid is moving through the pipes. Okay, so velocities over 2 feet per second are worthy of noting, and I have 3 in brackets here, and I'll talk about that at a particular time when I get to that slide. But that's another contributing factor, moving the fluid through a certain portion of the pipe too quickly. Okay, and then we got the chlorines, chloramines, fluorides, all the other things that are being added to our water when it comes into the building. And then, of course, we take it and heat it up after that. One of my little pet peeves, and most of the time I will argue this, there are some exceptions, but we really don't want to let the domestic hot water circulator just sit there and spin 24/7. It's not a good thing. It's part of the contributing factor. There might be some issues and some special situations out there where you must, and that will be probably dictated with codes and standards and that sort of thing. But for the most part, we turn the circulator on, we do the job it needs to do, and we'll get into this later if that doesn't make sense to you, and then we shut the circulator off. Generally speaking, that's the right approach. Now, everybody that's on this this webinar right now has the ability to control the velocity and continuous circulation. Those other two things, the elevated water temperature or the chlorines and chloramines and fluorides and all the other stuff that might be put in there, we don't have control over that. But we can slow the water down, we can size the pumps and pipes correctly, and we can control those circulators appropriately as well. So that's, yeah, go ahead.
We had a question from Darren. He was wondering, could dual systems be a contributing factor to the elevated temperature?
Dual systems. I need another explanation of what dual systems mean.
We'll wait for Darren because I don't know either.
Well, we can catch it when it comes in. Okay?
Catch it later, sure.
Yeah. So let's talk about some design considerations. When somebody's looking at putting a system together, either a full-blown remodel where they're ripping out old and putting in new, or brand new construction. These are the things we want to talk about, okay? This just goes back to the basics, right? This is circulator sizing 101, okay? We need to know what the GPM is. Once we know what the GPM is, we need to know what the resistance is going to be to that circulator that's trying to push that specific GPM through the system, the pipe, the valves, fittings. So it's either friction loss or pressure drop, feet of head. Those are the two things we need to size pump. So let's break that down, starting with the most important is, where does this gallons per minute come from? What is our target? What's our bullseye within that target? I'm going to list some things here. You'll see what it totals out to, but these are all considerations for coming up with gallons per minute. The first one is, and generally the plumbing engineers will look at this and say, I'm going to figure out what the line losses are, or the heat loss of the supply portion of the system out to the hot water fixture. So most people understand that. If they do it this way, that absolutely, well, let me clarify. If they do this correctly and their numbers are spot on, then that gives us the absolute minimum flow required so that we can overcome just the line losses. That'll be a continual GPM requirement. You would have to run the pump continuously if you strictly use number one as your guide for coming up with gallons per minute. Number two, how quickly do we purge the lines? Now, this goes to say, if we shut the circulator off and we turn it back on, how quickly do we need to evacuate all that tepid water and bring that hot water system back up to a usable temperature? Okay, so that's number two. That's a consideration, and that's a calculation to figure out what the GPM needs to be. Number three, of course, is we've got to worry about this maximum velocity limitation based on what the material within the system says. Now, these are typically the piping people, right? These are either Copper Development Association, or it's going to be Plastic Piping Institute, or whoever everybody got together and said, let's sing off the same sheet of paper. So that's those are limiting factors, and you'll see that as I bring those up as well. Number four is, well, how are we going to control the pump, right? What control strategy are we using? I'm showing up here in the upper right-hand side, just a PLC, a programmable logic controller that could be used on some commercial applications. Taco has a nice little device called the Smart Plug that just turns on the circulator and turns off the circulator at appropriate intervals based on what the needs are. That keeps the lines loaded up with hot water, yet does not run the circulator continuously. Number five, we got to look at these things, other things within the system. We'll look at this actually a couple ways. For now, most of these mixing valves or mixing stations have a minimum flow requirement in order to meet their accuracy quote. They're saying they're going to be accurate within 2% of one way or another. Those accuracies are contingent on meeting a minimum flow requirement. So if you're using these devices and you want them to work the way they're expected to, then you want to try to look at what their minimum flow requirements are. Then on number 6, this will be my last one. If you folks are using tankless style domestic hot water generators and they're flowing directly through the units and not using storage tanks, then most of the manufacturers of these devices will have a minimum flow requirement while making domestic hot water. Some show this in writing. Some others you have to dig a little bit to find out what this is. Generally, it's not just the minimum flow to cause these things to fire. In North America, it's generally around a half a GPM. When we're talking about using these things for domestic hot water circulation, then they will give you a prescribed minimum flow amount. So as you can see, one of those 6 things are going to drive what that GPM number is. So this is my guideline. I start asking these questions and then I come up with GPM. Once I come up with GPM, then we'll talk about what we do with that from there. Any questions so far, Mark?
Yeah, well, getting back to the one from Darren, so he clarified, so he was, as far as dual systems, he was meaning hot water tanks with space heating applications as well. So wondering whether that could be a contributing factor to the elevated temperatures.
Okay, a combination device that does heating and hot water. Okay, and the question was in regard to that, I'm sorry?
Could it be a contributing factor to elevated temperatures?
Oh, it could be. Absolutely could be. But that's when we have to consider some of the things like we just showed you, mixing valves, stations, and stuff that keep the water level temperature down. Now, remember, if codes start requiring 140 or 60 C out in the wall, then you're going to have to rethink what you're doing. And based on people I'm talking to, based on Legionella issues and not having to do dosing with chemicals and such, we're probably going to try to take care of this with temperature. And 60 C, 140 F is probably the number. So we're going to have to work with that. Okay. Again, don't believe me until you see it come out in paper. I'm just letting you know what I'm hearing in the background. So, all right. So what are the fundamentals of these little circulators, right? What's the job description? What's the responsibility of a circulating pump? Okay. Again, this is where a lot of people miss it. The responsibility of a circulator in a domestic hot water circulating system is merely to have the water there. So at the fixture, so that when they open the faucet, it just comes out hot, right? It's people have misinterpreted this. We actually have had some folks using, Hunter's curves, water fixture unit count loads in GPMs for size in domestic hot water circulators. And guess what? That's incorrect. So understand, all we're trying to do is move water around in a circle so that it stays warm in the pipe, and they walk up to the fixture and open the fixture. Therefore, just the pressure differential from whatever's inside the pipe to atmospheric standing at the fixture is what gets water out of the pipe. These are not mini hot water boosters. And believe me, folks, we have seen that in the design process. And we're trying to make sure that doesn't happen. So again, I'm emphasizing that for a reason. Okay. So what are other fundamentals? Well, how much does the pump actually need to produce? Well, I kind of gave you 6 things to look at. Okay, that helps. Most people will generally look at that heat loss or line losses of a system and kind of come up and make sure they can meet that. And that's one hurdle they got to make sure they get. But based on my experience, one of those other 2 through 6 is going to set the GPM number. As long as they're insulating the hot water piping system and its dedicated returns, generally speaking, the heat losses will be your lowest GPM number if that's all you're going to use as your criteria. So again, typically we want to move the water faster. We're going to bring the circulator on, we're going to let it do its job, and then we're going to shut the circulator off. And that's going to mean pulsing the circulator on and off. And this is nothing that's happening in a rapid means. We're not going to fast cycle the pump to an early grave or anything. We bring it on for a few minutes and we shut it off for longer. We bring it on for a few minutes and we shut it off for longer. And that's perfectly acceptable within the circulator manufacturer's world. Okay, nothing wrong with that. So again, is getting the dedicated or common return line piping size and circ size important? Well, of course it is, right? And so let's jump into where some of that comes from. I'll stop real quick, Mark, and see if anybody wants to ask a question.
Yeah, I don't have any questions right now.
Very good. So let's look at the Copper Development Association. I'm not going to read all this for you. I'm just going to highlight a couple things. There's that number again, 140. Okay, and they're also pointing out, talking about lowering the velocities to 2, 3. So they're giving you a little range from 2 to 3 feet per second within a certain portion of the system. And I will remind everybody what portion of the system that is referring to. Another point here is the locally aggressive water condition comment there. They're not talking about hard water. They're talking about the chlorines, the chloramines, the fluorides, and all the other things that are being put into the water when it's cold or at ground temperature, and then we turn around and heat it up. It makes it more aggressive. Look at this next highlight here. Due to constant circulation and elevated water temperatures, blah, blah, blah. Do you suppose they're talking about closed loop heating or cooling applications? Not likely. They're talking about what we're talking about right now, and I'm saying that because who would ever run a circulator continuously through without a call for heat? You know, I realize some commercial applications might do something like that for various reasons, but I'm saying my interpretation of what this reads out of the Copper Development Association is talking about people plugging in domestic hot water circulator lines and letting them run 24/7. Okay? We're concerned with both the supply and the dedicated return side of the system. However, the supply side of the system is generally sized on those Hunter curves, those water fixture unit loads. And generally speaking, those are oversized. Those are not undersized. Again, more to come on that on another training where we're talking about something that's called right sizing. And I coined that, I'm quoting Gary Klein, who came up with that term. But generally speaking, the problem lies when we see some of this either oxidation to plastic piping, or we're seeing velocity erosion corrosion with copper piping. It's happening on the dedicated return portion of the system, not on the supply out to the fixtures. And then this last part, I'll read the whole thing because it kind of brings it all to a head. It says care should be taken to ensure that the circulating pump is not oversized and that the return piping is not undersized. Both are common occurrences in installed piping systems. And, you know, we don't see this happening every day, but this is kind of the Copper Development Association's get out of jail free card. Somebody's not going to pull out a bunch of pipe that's got holes in it, bring it back to the wholesaler and say, I got defective material here. They try that with other products, and that's going away as well. But just understand, this is where a lot of this information is coming from. It's the piping people that are saying, be careful, okay? Let's put a number to it. I just said, I gave you velocities that the Copper Development talked about, and they said from 2 to 3 feet per second. And this, again, will be one of your handouts. I've got it labeled as copper type M 3/8 to 3 inch, okay? And you can see the column that says 2 feet per second. You got the same thing in type L down here, 2 feet per second or 3 feet per second. Let's grab a piece of 3/4 inch type L and say, folks, if you're conservative, you better keep the velocity in that line to 3 gallons a minute or less. Okay, that's being conservative. That's staying at the kind of the common ground of 2 feet per second. Now, because they put this in writing, they're allowing you to push that to 3 feet per second, which translates to 4.6 gallons a minute. Does everybody get that? Mark, I'll give you a second if somebody doesn't understand. this little lookup table.
Okay, I'm checking. Nothing yet.
Okay, cool. So now let's talk about flexible piping systems. This comes out of Upanor's manual, but the good thing about it, the Plastic Piping Institute for North America has pretty much decided this is kind of where we're going, and this is the first newest thing I saw on it, so I captured it, put it on here, and so that's why I'm referencing it. I believe most people selling flexible piping systems in North America belong to the Plastic Piping Institute, and for the most part, they're singing off the same sheet of paper. So let's look at this. So you can see the system.
I do have a question, Rick.
Okay.
What is the difference between type M and type L pipe?
Okay, that's the wall thickness. Again, the OD of the pipe is constant. The ID changes with the thicker wall. There's generally speaking, there's M, then there's L that's thicker, and then the thickest is type K. I didn't even list K because most people aren't using it. So hopefully that.
Another question. Another person asked, could you kind of go over that chart one more time, a little bit?
Which chart?
Though I think it was the one you were just at because you asked about
this one right here.
I believe so. I'm not 100% sure, but I believe that's what they were.
Okay, so we've got a lookup table. It gives you type M copper and type L copper in various sizes. You look here, and it says 2 feet per second, and it says 3 feet per second. We're speaking of the maximum flow in the re-circ portion of the system. And again, you'll get a copy of that as part of your handouts. So let's look at system type, and let's go over this first one. Cold water piping, 4.2. They're telling you to look at table 4.2, but they're telling you you can do 10 feet per second. Cold water, 10 feet per second, just reference table 4.2. And notice down here in closed loop heating and closed loop cooling applications, they're also referencing 4.2. So let's go ahead and look at 4.2, and that's your standards reference, right? That just says as the temperature goes up, the ability of that pipe to handle higher pressures goes down, okay? And the bold lines are your standard, your ASTM standards, generally speaking, okay? And again, that's what, if it tells you to reference 4.2, I just want to show you what that's about. We're not going to focus on that. We're going to focus on the domestic hot water piping, and I will add the word supply. Okay, so you got 140, 80 PSI, and 8 feet per second. That is the supply out to the fixtures, which generally is always generously sized based on water fixture unit loads and code requirements, etc. That's usually not where the problem lies. The problem lies in the dedicated return lines. Okay, notice same temperature, same pressure. They want 2 feet per second in that portion of the system. So again, I'm doing a demarcation so you guys know that the supply portion of the system is treated different than the return portion of the system. Okay. Here's that same lookup handout that you folks will get. Notice the only thing missing here is 3 feet per second. They're just saying, let's stay conservative. Let's use 2 feet per second. We've all agreed on it. So if I got a piece of 3/4 inch DR9 PEX, then I'd want to stay under 2.2 gallons a minute. And in fact, if you folks want memory type stuff, 1 gallon a minute for 1/2 inch, 2 gallons a minute for 3/4, and 3.5 for 1 inch. So, and those generally are sizes that are used in dedicated return lines. So everybody good so far?
Yes.
All right. So we did GPM. What's next? Well, once we know what the GPM is, we can calculate based on the pipes, the valves, the fittings, and heat exchangers and everything else. And we can come up with a real number. Notice I said real number, not a wild ass guess. That we call that, you know what it is, right? And people that use valve and fitting factors are just guessing. And the people in this industry know better. And there's plenty of tools out there to do a better job. And so I'm going to give you a couple of suggestions. Okay, here everybody's got these. This is to us from the Copper Development Association. It says if you're running a certain GPM over here in this column, and you figure out which pipe and type, and we'll give you an idea what your pressure drop is. In this case, 3/4 type L, at 3 gallons a minute is 0.011 per linear foot. Okay. And that's in PSI gauge. Okay. So we just do the math, right? There's per 100 foot, 1.1 PSI. We convert that to feet ahead. That magic number is 2.31. You take your PSI times 2.31. That'll get you converted to feet ahead. In circulators, we're still doing feet ahead. In pumps, we're doing PSI. So again, maybe someday we'll all just drop back to a pressure instead of an old term for open systems. But at this point, we've got to deal with it. Okay. Any questions?
Not at the moment.
All right. So valve and fitting factors tend to be a little bit more accurate. In fact, my experience is much more accurate than valve and fitting factors. So, and it's simply this, pick a size, start doing a takeoff of the fittings within that portion of the system, and we can come up with an equivalency of straight pipe. This is not rocket science. We just round these numbers up and we add them up and we add that to the total run. Okay. So in this case, we measure the pipe and then we add 70 additional feet to figure out what the additional pressure drop would be to make sure we cover our fittings and check valves and ball valves and that sort of thing in this system. So that's just using equivalency charts. And those are available from lots of different manufacturers. This is one from TACO, but the people, the Copper Development Association or Mueller, Streamline, all those people, they have equivalency charts, I would imagine, as well. So, personally, a couple of software programs I use. Here's one that Siegenthaler's has had out for a long time. This is for purchase. And then our good competitors at Bell & Gossett have had this out for many years. I use Siegenthaler's for Type M. I use Bell & Gossett's for Type L when it comes to copper. Okay. When we're talking the flexible piping systems, well, the Plastic Piping Institute has a nice little calculator out there. You folks want to make a note. It's just simply plasticpipecalculator.com. And you put your type of material in there, your ASTMs, your SDR9s, your pipe size, your flow, your length. Is it just water for potable? It would be, let's hope. You put your temperature in there. You can even put your fittings in there if you know what your equivalencies are. And then it just spits out down here at the bottom. Once you hit calculate, it spits out what your PSI drop is. We convert that to feet ahead for you. We show you what your velocity is. Again, this is a handy little tool to come up with the second part of sizing a circulator correctly. Other considerations, of course, are the mixing devices. I already mentioned that based on minimum flow, but we need to know what the pressure drop at that minimum flow is so that we can size the pump appropriately, as well as the tankless water heaters. We need to know if we're running directly through those with the recirculation line and we're pulling through the heat exchangers, we need to know what those pressure drops are as well. So hopefully that helps you when that's concerned. Let's see if there's any questions on that, and then we'll jump into the piping and design and layout.
We're good for now. Right.
Very good. So let's just talk about some terminology and then show you some real simple conceptual sketches, folks. There's a whole bunch of stuff missing here, but I'm going to try to highlight the important parts and make sure that I get my point across, right? So what we're talking about is a trunk and branch system with a common return, single circulator with balancing valves. I'm talking about the balancing valves up here, right? I've got 4 of them. They're taking these floors or zones, we can call them zones, and those zones are coming back to a common header and then coming back to a circulator. Most everybody understands that, and this is very common. We've seen this used, and we've seen people play with this in more ways than one. Okay. Again, it's just one way I'm going to show you. I do have to point out that, if we look back at these balancing valves, where do they belong, right? How do I get to them? I'm showing you a couple of examples here, right? But it is something that has to be looked at. I've got to get up and down on a ladder, depending on the style of balancing device I'm using. I've got to go back and rebalance, and how problematic is that? And again, I'm leading you a certain direction here. I'm leading you toward a better solution than what's currently out there. Bear with me as we go along. I heard this, I got it in quotations. I heard this from Siegenthaler, and it didn't have to do with potable water at the time. I'm sure he still speaks of this, though. And a balancing act, what does he mean by that? Well, does that sound like something that's easy? Not necessarily. So it is a balancing act. We got variable orifice style balancing valves out there. We got fixed orifice style. For those who don't know the difference, is when I split the actual pressure points here with the actual balancing device. That's called a variable orifice. When both of those measuring devices are on one side of the balancing device, then it's a fixed orifice. There's other things that have come to town and have worked quite well. These temperature fixed applications that use basically little throttling well, I guess you'd call them cartridges that actually are trying to be a set point control. They're saying, hey, if you want this to be 120 degrees Fahrenheit, then that's what it's going to open up for. As soon as it is, it starts to close down, and it just tries to maintain a temperature within that. Of course, that requires the pump to run 24/7 in order for those to work appropriately, generally speaking. Okay. So here's one thing I want to throw at you, because most people forget this. It's been done in the heating business for many, many years. Does anybody realize that you can use a little tiny high efficiency circulator to accomplish the same thing? This next slide kind of lines this out for you. Okay. What does a balancing valve actually do? Well, it's going to shoot for specific GPMs or a specific temperature, correct? Okay. And if you're going to use any of these devices, do they have to be NSF listed? And the answer, of course, is yes. And do they need to be accessed or serviced? Well, if they have water flowing through them and they tend to get gummed up and they need to be serviced or fixed or changed, of course they need to be accessed and they need to be serviced. If that requirement is there, wouldn't it be nice to have isolation on each side so you don't have to take the whole building down, and to have some kind of union so you can take it apart in these tight little places that we put all this stuff? Now, again, I'm just saying, ask a question, give me the answer. The answer is yes on all that stuff, right? If I'm doing multiple zones or multiple branches, I have multiple branches coming into a common header, do I need a check valve? The answer is yes. My point being this: if I buy these type of devices and put them on all of those branches and I comply with all these 4 things I just listed, those things get really expensive. Guess what? We have a product been out a long time that can accomplish all of those things and still get you within your budget. So just food for thought, okay? Now, let's talk about what people have done with balancing valves and high efficiency ECM circulators. They're kind of saying, hey, let's try this and see if it works, okay? What I mean is we now have these dynamic balancing valves that open and close automatically, generally based on temperature, but they require the circulator to create the pressure differential 24/7. They generally will run these circulators nonstop, and these valves will squeeze open and close to give you a set point temperature. Do they work? Absolutely, they work. They do a great job. It's a great concept, and these things work. I am saying this is a way of doing it. It is not the only way of doing it. And one thing I will bring up is generally they will tell you to put these high efficiency ECMs in one of the adaptable auto modes and just let it figure it out, because they've sold these devices as smart circulators. Now, I did that with air quotes for those who didn't see that, but there's not a product on the market that's in a form of a circulator that is smart. If you set them up in the wrong mode, they do not automatically fix themselves. Heads up on that. The word smart circulator should be stricken from the library, okay? Here's what they do. These are the adaptable auto modes. Everybody's got them. The big five in North America all have something. They've got a special name for it one way or another. Guess what? The algorithm for these things was never written around domestic hot water circulation. And until it is, I would say these are to be avoided. The main reason is, how can you be assured that you will not exceed the maximum velocity limitation that we just talked to you about? That's not a TACO or a pump thing. It comes to us from the people who make the piping that we're using within our systems. So heads up on that, okay? Again, these are Delta P type circulators. They require pressure changes downstream in the automatic modes in order to make a decision to speed up or slow down. Now, that's not the same type of pressure changes you're going to get. You put this on a circulator on a domestic hot water circulating system, you got people opening and closing faucets, and that's going to change what that circulator is feeling. And it's going to be ramping up and ramping down and doing wacky stuff it was never meant to do. And again, think about the big picture here, okay? I think I made that point as far as people using faucets and stuff. What we're saying at TACO is it makes the most sense. Set the circulator up in a fixed speed or fixed GPM application that gives you the GPM you want, and let that thing run and then shut it off when it's done doing its job. Bring it back on again and then shut it off when it's done doing its job. Its job, as a reminder, is to keep those lines up to temperature. Does not need to run 24/7 to accomplish that task. Any questions?
Yes, I have a question. So from Darren again, I'll read it to you. So I normally design hydronic systems, but every so often I get a retrofit re-circ pump sizing call. In that case, I go to the generalization charts in a TACO binder that I've had since 2007. Is that still a good chart to reference, or is there something out there that could help me with fine-tuning a re-circ pump in retrofit applications?
Sure, that handout I just gave you would be your first start, because it tells you what the GPM is, right? If you got a retrofit situation, you already know what pipe size you got. If you know what pipe size and type you have, there is your GPM maximum. You want to be under that. So there's the first half of sizing that circulator. Then you use the tools I just showed you to figure out what the pressure drop's going to be. And once those are considered, now you can appropriately size the circulator. So the old charts were there with general recommendations, not knowing what the specifics were of the job. So now that you know what you know, you can't unknow it. So you got to measure pipe, you got to know what your fittings are, and you've got to come up with a concept. If we have enough time, I'm going to show you some neat things that TACO can help you do. I mean, we can actually go into the circulator and set the circulator up at a specific GPM and keep a record of it. Once once the circulator's in the system, we know absolutely what the resistance of that system is, because now we can see it plotted on a chart. And that's all done with Bluetooth and some cool ways of doing that. So I'm going to move on. Okay. Remember this concept? This is other ways of looking at it. Here's kind of an isometric view of what a loop is. Okay. It's a different way of looking at domestic hot water initial layout. Okay. I call this a full size loop, and it would be if it was, in light commercial applications down into high end residential applications, where if it comes out of this water heater and it's 1 inch, it's going to stay 1 inch for the entire run of that loop. Okay. If it's 3/4, it's 3/4 for the entire. When you get up into 1.25 inches, 1.5 inches, so on and so forth, then we will drop down on that line size to something that's appropriate based on what we've already talked about. But this is more, again, just a conceptual idea of how to relook at the way you do your domestic hot water layouts. We've got these strategically located little tiny manifolds or T's with short drops or short risers that will deliver our hot water in those desired, remember I said it'd be a perfect world if we get hot water in 5 seconds. Well, this makes it a lot more able to do that when the only thing you're evacuating is the drops and risers. Anyway, that's concept. I'm just nailing the concept down. Here's a view, a bird's eye view, plan view of what we're talking about, coming out of the heater, swinging over and serpentining close to the fixtures that you're using, and dropping or rising up to the units. Most of everybody's got this type of material that can do this. Even the copper people, there's copper manifolds. I think Alberta Tees, a Canadian company that makes products. There's probably other ones out there that makes little tees that you can cut in line. So this could be done with hard pipe. It can be done with flexible piping system as well. Here's a kind of an idea of just like a little apartment building that I just drew up as a quick reference, okay? Notice this would be your traditional trunk and branch system, right? Where I'm coming up and I'm going out and teeing off and picking up these systems and with drops or risers. And then I've got a dedicated return line that's going to come back and take care of that. So everybody hopefully conceptually can see what's going on there. What I want to show you now is an alternative. Okay. Now you can see that now I'm bringing up an appropriately sized hot water line, and at the end, and I'm serpentining this so it's real close to everything that's needed there, and then I have the dedicated return line for that particular zone, and then I do the same thing over here on the other side. So hopefully that makes sense to you. With that in mind, now I've changed my drawing a little bit so you can see how this is no longer trunk and branch, but it's a loop style configuration where I have appropriately spaced and set manifolds strategically out to pick up with short risers or short drops the fixtures. Now this is back to showing balancing valves. I'll give you an alternative for that as well. Okay. What if I were to take those returns and not tie them together up in the building, but bring them down individually in their smaller line sizes and do the balancing right here in front of where the water heater's at? Again, concept that if it can be done, which it can in some cases, actually many cases, I can sit down on a bucket right now and do my balancing here. No more up and down on ladders, no more crawling on your knees at access panels, etc. Okay. These are concepts I'm giving you at this point in time. Now, here would be the same thing, but in lieu of balancing valves, what do I have here? Okay, remember, we already shared the concept with you. I have a variable speed circulator that I'm manually setting the GPM on. Okay, I'm not letting it operate automatically, but I'm setting that circulator to what it needs to be. So anyway, what if I brought those all the way down? Like I said, I'm extending these drops back to a close proximity of the water heater. Okay, and then I can sit on a bucket and I can adjust those. I've got some details I'm going to show you here in just a second. That'll if the stick drawings, the little conceptual black and whites don't work for you, I've drawn some stuff up in Visio as a detail that give you a better idea of what we're talking about here. Let's stop right here and see if there's any questions.
Yeah, I think Darren just followed up with that original one, said he probably needs to start asking the contractors about that. But Marydale had a question. I wasn't quite sure what it was. I was trying to clarify, but I think it was wondering whether tankless water heaters can be used for both commercial and residential applications with this.
Yeah, that'd be a question for them, the people that make those. But based on what I've seen, absolutely, they make them for both full-blown commercial applications as well as residential.
Okay.
So here's where the second to the last application sketch. It's kind of the same thing. You notice I'm bringing the risers back to centrally located close to the heating device here. And I've got NSF listed balancing valves on there. Again, every one of those would have to have isolation. They would have to have check valve. They would have to have unions. They have to be NSF listed. I think I said that already. My apologies. But understand that when I start pricing those out with all of that stuff, they're fairly expensive, at least easily within a range of these small circulators that I'm referring to right now. So just a heads up on that. So the next sketch kind of shows you the change up on that, right? Same thing, but now I got a circulator. Now I can sit in front of each of these circulators. I'm showing, I believe there's 12 in this application. I could sit in front of those 12 circulators in one appropriately sized manifold and now adjust each of those to give me the flow I need in order to keep the each one of those zones on each of those different floors at the appropriate temperature. Boy, this gets real handy when it comes to the initial balance of the system and subsequent pump change outs or anything along those lines. If I'm just servicing or if I've got an issue, well, I am dealing with one line set and one circulator, and I can adjust it up and down to give me what I'm looking for. So anyway, again, these are conceptual ideas at this point, and I want you to realize this. This is doable. Okay, here's those details I was telling you about. Okay, I'm just making sure that there's a couple things that I'm going to address here. In this way, I've got the ability to purge all of these independently by shutting off these two and opening this one and purging here with this valve closed, or to go ahead and put the actual purge drains on each of the zones coming back. Does that all make sense to you? Is there any clarifications on that? I'll give you a second. I've got some more sketches as well.
No questions at the moment. I have about 6.5 minutes left in the presentation, and from a timing perspective, though, just to keep you up to date. But we started a few minutes late, so I don't mind extending it a little bit because we did.
Okay, I appreciate that. Yeah. Here's the same thing, folks. Just showing it with the consideration of a mixing station in there. Just remember, when you're doing domestic hot water circulation, a general thing to get your arms around is you always have to split the flow. The flow has to go to the heating device, and it has to go to a mixing device when there's one in there. So that's just heads up on that. So,
I do have a question. I do have a question for you.
Okay.
Have you heard of less erosion issues using IPEX Aqua Rise piping?
No, can't speak to that at all. No. This valve is just a detail I wanted to make sure, folks. Number one thing that burns up any domestic hot water circulator is people not actually flushing all the air out of the system. And you've got to have this set up, whether it's the way I'm showing you here, or there's devices on the market that can do it for you. But that's a number one thing that'll kill any color, any brand circulating pump, is to sit there and run it dry. And these are not fans. They don't move air out of a piping system. They move water. Okay. So heads up on that. Make sure they're in all your details. Okay. This is will be another one of your handouts that could be available. I didn't send it at this point. All this is, though, is just a takeoff sheet I use to actually tally things up and get an idea of what the system really requires. Another thing that I want to show you, just a heads up on, is a domestic hot water size right circulator sizing tool. That's a real long name. I'm going to try to get that shortened. But right now that's available to you on takocomfort.com. And it's pretty handy. You just put some of the same information we just talked about in there, your supply line sizes and lengths, your return line size and length, and it spits out GPM and feet ahead. Gives you some flexibility in the summary down here to handle mixing valves and valve and fitting factors and or additional pipe lengths, and does some handy things for you. This is the residential version that goes up to 1 inch now. Hopefully before I leave, in fact, I'm retiring at the end of the year, I hope to be able to introduce the light commercial version that'll go up to 3 or 4 inch. It'll be real handy. It'll do the heat loss for you and everything. So keep your eyes peeled on that as well. Let's get into product, because I just showed you what needs to be considered. Let's show you some solutions. This is our little 006E3. The cool thing about this little pump is that it has a little dial on the face of it, right? I can turn it anywhere from its low setting to its high setting and anywhere in between. This is not a multi-speed pump. This is an infinitely variable speed pump between 4 and 44 watts. Okay? And you get lots of choices in how you want to adapt. This is that very popular BSP. This is 1 inch BSP or G1 thread. Lots of different things in our industry are coming out with this thread. Pretty handy, worth consideration. This is the curve of that particular circulator. Again, anywhere between 4 and 44 watts. And this is how we show people where to set these things. These little demarcations, max, high, medium, low, and minimum, are just showing you where to appropriately set the pump depending on what you have within your system. Okay. If you got larger systems, we go up to 300 gallons a minute, folks. So again, that's not domestic hot water re-circ by any means, but that would be a good transfer pump from like a large boiler to a large storage tank. If you got a good size domestic re-circ, then we've got sizes in the realm of the 0034E plus. And then I want to highlight the 18, and you'll see why here just real quick. It does have a dial. You can do anything you want manually with it, but it also has Bluetooth communication. Gives you 4 different modes of operation. I've already spoke to this, and I'll emphasize it again. The only mode of operation, regardless of what the pump has on it, that you want to operate domestic hot water circulation in is fixed speed. Fixed speed gives us ability, as you can see, to set the GPM. You will see what the head is just as a result. This is a resultant number. It'll show you what your wattage is, and it'll show you what your RPMs are. What's even best about this little hamburger thing here, I'll click on that. That gives me a printout. It gets PDF, keep electronic copy of my operating point with GPM, feet ahead, and I can take a picture of the job, tells me where the job's at, tells me who did the job, etc. This has all been available for several years now. I think we probably in the neighborhood of about 5 years that we've had this available to you. And maybe you don't know that. So that's another part of this. There's tools out there from various manufacturers that make sure that we can do these jobs better than we are currently doing. So in closing, hey, think about your systems more. Think about the loop staying very close to the fixtures. This whole serpentine loop concept in lieu of the traditional trunk and branch. Okay. And then those 6 things I listed, I know that's like a lot to remember, but I think if you think back on it, it's pretty easy that those all have to be considered in order to come up with the gallons per minute. Okay. And then be careful, right? We want less wear and tear on the system and its components. So that's why the piping people have given us these maximum velocity limitations. Just stay at or under those, and you'll be a lot better off. You won't have to worry about creating sprinkler systems where they weren't supposed to be. And then, of course, consider using circulator. And I'd love anybody for a comment to say why you couldn't use a circulator in lieu of these fancy balancing valves that are out there and been out there for a long time. So anywho, any last questions? Again, I got done in time, even though we got started late. I'll do that for the other people that are going to be teaching their class. So Mark, I'll let you close that up. Do whatever you need to do.
I appreciate that, Rick. Thank you very much. We just had one comment from Darren. He wanted to say congrats on your retirement, Rick. So he actually met you with Red Deer when you came through one time with Sean Gyverson.
Well, I'm back up there in a couple of weeks, actually. So.
Okay. Well, cool. So any other final questions for Rick? I will point out that you guys all have access to this presentation. You can go onto our website and rewatch it at any time. I think it still stays there for the next 30 days or so.
Great.
And then we will also we will put these presentations also on our training site, trainingtrades.ca. And we will also, in our next issue of Plumbing and HVAC, we will have basically a summation of this presentation as well in our next issue too, with the link to the video. So but you obviously can come back and reference it and go closer, but also make sure you take those that PDF that we put on there for you guys as well, that Rick provided for your references. So, but I don't see any other questions. So thank you very much, Rick. I really appreciate your time and great presentation. And we're getting a bunch of thank yous on the chat. So I guess we'll head into our next presentation from Mitsubishi, and then you guys will have a little break after that one. So, but they're probably ready to start. And but thanks, and we'll see you soon, Rick.
So long.
All right.